Hello, my name is Caleb Keener, and this is my Physics 2211 Lab 3 black hole. To begin with, the purpose of this lab was to find the mass of a black hole by analyzing the orbit of a planet around it. We then use this information to determine the initial velocity the spaceship must have when it leaves the surface of the planet to fly around the black hole without crashing on neither the planet nor the black hole. Some fundamental physics principles is Newton's second law of the momentum principle and Newton's universal law of gravitation. And then here's a preview of my lab results with the mass of the black hole and the initial velocity of the spaceship. Some main physics ideas we use in this lab is the universal law of gravitation, which you can see here as f of g and the absolute value of f of g. And then we also have Newton's second law, which is F net equals dp over dt, or F net equals F net parallel plus F net perpendicular. And then we also have the velocity update and the position update. One major assumption in this lab is that F net equals F of g. So some reasoning is that due to the fact that this scenario is in space, the only force acting on the planet is the gravity of the black hole, and the only force acting on the spaceship is the gravity of the planet and the gravity of the black hole. Forces are not constant in this situation, so final velocity is equal to average velocity. As well, F net parallel is responsible for increase or decrease in speed, and F net perpendicular is changes in direction. So here are some initial conditions when finding the mass of the black hole. You have the gravitational constant, the mass of the star. Time starts at t equals 0, and the time between observations is 1 day. You also have the system as a black hole, and the surroundings is the planet. Continuing on, this is my glow scripts code that helped me determine the mass of the black hole. As you can see, all of these are the values for the planet. So you have v initial, v final, momentum initial, momentum final, and you can see how I calculated each of these. And it keeps evolving, and I keep deriving things until I have derived everything I need, F net, where F net equals dp dt, and then this is the equation I use to calculate the mass of the black hole. And one thing in my code that I did include was that I have a running total of the mass, and then over here I divide that running total by how many times the loop ran to get my average mass. And continuing forward, you can see that my results, F net equals this number, F net parallel and F net perpendicular add up to equal that. And the mass of the black hole, as shown through the code previous, is 1.26104 times e to the 34. And as you can see, my planet made one full orbit. So the velocity of the spaceship, in this part, the system is the spaceship and the surroundings is everything else, which means the planet and the black hole. As you can see here are my constants: black hole mass, the gravitational constant, planet mass of the planet, mass of the ship, delta t, and t equals 0. And here you can see that I've defined the planet velocity and the planet speed, as well as the ship's speed in the xy direction and the ship's velocity. Continuing forward, when I calculated net force, I calculated the force of the black hole on the planet and the force of the ship on the planet to get an F net on the planet. And then I calculated the force of the black hole on the ship and the force of the planet on the ship to get an F net on the ship. And because of this allows me to both graph the orbit of the planet and the orbit of the ship to both visualize. And right here is my planet and ship velocity and position update formulas, which I stated earlier. And this allows me to update the position at every increment. So here is my results. As you can see, my spaceship did not hit either the planet or the black hole, and it got surprisingly close to the black hole. My initial velocity was this, and the closest distance between the spaceship and the black hole was 2.3688 e to the 8 meters. So what does it mean? Discuss how the net force and its parallel and perpendicular components are different from the rate of change in momentum and its parallel and perpendicular components. Net force is the same as the rate of change in momentum, and each parallel and perpendicular components are equal to each other. This is shown in the code when F net equals dp over dt, and it is explicitly stated in the momentum principle. Continuing on, what if? So for this part of the lab, we had to answer what initial velocity would our spaceship need to have in order to enter some kind of orbit around the black hole. So I concluded that the ship should have a similar velocity to the planet with a greater velocity in the y direction and an x velocity in the negative direction that is smaller than the planet's initial velocity. So my initial velocity for the ship to imitate an orbit is negative 4.5 e to the 6 in the x direction, 9.2 e to the 6 in the y direction, 0 in the z meters per second. And although my ship did not make a full revolution, the lab does state that we must make our best effort even if we do not succeed at no point. Thus, I made my best effort, and I did imitate a half orbit around the black hole.